If we're going to prove what is commonly known as the squeeze theorem, it says that if f of x, well, let me not, okay, if f of x is less than or equal to g of x, which in turn is less than or equal to h of x, and the limit as x goes to a of f of x equals L, and their left one, and the limit as x goes to a of h of x is also L, then this jammed in between must go to L. Then the limit as x goes to a of g of x is L. Okay, so proof. The limit as x goes to a of f of x equals L means given any epsilon greater than 0, there exists a delta 1 such that f of x minus L is smaller than epsilon whenever x minus a is positive and less than delta 1. So now, let's just rewrite this a little bit. Let's remove the absolute value bars here. This means that f of x minus L must be between negative epsilon and epsilon whenever the absolute value of x minus a is positive and less than delta 1. So this is a key part. Now so we dealt with that. And we're now going to deal with this. We're going to do exactly the same. A little different, but almost the same. The limit, well, okay. So, I'm going to do exactly the same. The limit as x goes to a of f of x equal L, that implies that given any epsilon greater than 0, there exists the delta 2 such that h of x minus L is less than epsilon whenever x minus a, an absolute value, is positive but less than delta 2. Expanding this piece, this says that h of x minus L is in between negative epsilon and epsilon whenever 0 is less than x minus a, which is less than delta 2. And you know what? I want to add L to all three sides. So it's not going to change this piece. So you have L minus epsilon is less than h of x, which is less than L plus epsilon, whenever 0 is less than x minus a, an absolute value, which is less than delta 2. And I meant to do the same thing over here. I'm going to add L to all three sides. So I get L minus epsilon is less than f of x, which is less than L plus epsilon, whenever, so I don't change anything, 0 is less than this mess, less than delta 1. This piece, and I have this piece. Now, we can choose delta to equal the min of delta 1 and delta 2. Alright, so what this tells me is that this statement right here is also true for delta. And this last statement right here is also true for delta. It can be true. These statements are true for delta. That statement is true for delta 2 or anything smaller than delta 2. So what we have is L minus epsilon is less than f of x, which is less than L plus epsilon, whenever 0 is less than x minus a, which is less than delta. And we're also told that, we also established that this statement is true. Less than h of x, which is less than L plus epsilon, whenever 0 is less than x minus a in absolute value. And I can use, instead of using delta 2, I can use something smaller, like delta. Okay, so now let's put this together. We have that L minus epsilon is less than f of x, which is less than g of x, that's given, which is less than or equal to h of x, that's given, and h of x is less than L plus epsilon whenever 0 is less than x minus a, which is less than delta. Okay, now I'm going to rewrite this a little bit. I'm just going to get rid of this. L minus epsilon is less than g of x, which is less than L plus epsilon whenever 0 is less than x minus a, which is less than delta. But I have to say one thing important. And we had it at the beginning. Epsilon is any positive number. Ah, wait a minute. That's the definition. Okay, so now let's just rewrite this a little bit different. Let's take away L from all three sides. So we have given epsilon greater than 0, L, no, minus epsilon is less than g of x minus L, which is less than epsilon, whenever that's true. But this here is the same as, so what I'm writing is going to be the same, given epsilon greater than 0, this statement is the same as g of x minus L in absolute value is less than epsilon, whenever this is true. Okay, so now this is true. So given epsilon greater than 0, there does exist a delta, that one, such that g of x minus L in absolute value is less than epsilon whenever x minus a in absolute value is positive, but less than that known delta. But this means that the limit as x goes to a of the function jammed in the middle is f. Now, I guess I should have started off with some kind of a graphical argument. Suppose we know this. Oops, that's H. Suppose we know this. Okay, so let us graph this. The f of x is the lowest function. F of x, maybe it goes like that. Okay? And g of, now, let's suppose that's A. That is, we get L. F of A is L, or at least the limit is. In theory, there can be an open circle right there. And h of x, it also has the limit of A. But h is bigger than or equal to, what happened here? H of x is, come on, h of x is bigger than f of x, or equal to it. So it may be equal in more than one place, but pretty much it goes like that. And I guess I meant to draw A there. Now, f of x, g of x, has to be in the middle. It has to be in the middle. It can be crazy, but it's gotta touch at L, or the limit has to be L. It is, in theory, there can be an open circle right there. Okay, but the limits are all L. The limits are all L. F of x, it's the, as we get closer to A from below, is getting closer to L. From above, we're getting closer to L. H of x, as I get closer and closer to A, it gets closer to L from the left, and from the right, it gets closer and closer to L, and G is jammed in the middle. So let me just label this. So this is H of x, this is F of x, and G is jammed in the middle. So by the squeeze theorem, if F and H for some given L approach the same number, L, then F must also approach. G must also approach it. But nothing has, F of A can or cannot be defined in any combination for F, G, and H. F can be defined, but not the other two. G, F, and G can be defined at A, but not H. Any combination. We proved their squeeze theorem. Pretty neat proof. And all I did was use the definition.